Hey folks, Mike McDonald here again with you with yet another video. So I've done 6 in a row of the E6B videos, which are available in my playlist for E6Bs and in links everywhere. So I thought I would break away from the E6B and talk about a concept that I find that a lot of new student pilots find difficult to grasp. And that topic is adverse yaw. All right, what do we mean by adverse yaw? Okay, well, let's just review the movements and attitudes of an aircraft. Okay, you have 3 axes, all right? You have you have the longitudinal axis, which goes along the length of the fuselage, okay, back of the plane to the front of the plane. That's the longitudinal axis. It goes along the fuselage or the body of the airplane, okay? And so the airplane will roll against its longitudinal axis, right? And then you have the lateral axis, and the lateral axis runs from one wingtip to the other wingtip, left to right or right to left, along the wing, and the aircraft pitches around the lateral axis. All right, and then you have what they call the normal axis. The normal axis goes from bottom to top, okay, bottom to top or top to bottom, and the aircraft yaws around the normal axis or the vertical axis. It's sometimes called. So just to refresh your memory on the 3 axes, it'll help you understand adverse yaw. Okay, so what is adverse yaw? Well, it's when the aircraft yaws along that normal or vertical axis on its own volition due to movements that you make with the aircraft, okay, different attitudes that you make with the aircraft. Okay, so this aircraft is in space, it's in 3-dimensional space, and it's using control surfaces, the ailerons, the elevator, and the rudder to orient itself in various ways along these 3 axes, okay? So in the movements of the aircraft on these 3 axes by control inputs, you can have a phenomenon occur, which is called adverse yaw. Adverse yaw is yaw that you do not wish to occur and that affects the performance of the airplane, okay? So adverse yaw means the aircraft will either yaw to the left or to the right. When you make control inputs, it seemed non-intuitive that that would happen, okay? So there are 5 forms of adverse yaw that I'm going to cover today in this video. And they are, number 1, slipstream. Number 2, torque. Number 3, gyroscopic precession. And number 4, P factor. And number 5, aileron deflection. All right, so those are the 5 forms of adverse yaw that I'm going to cover in this video. So what I've done was I've gathered some images from the internet, which I'm going to flip to, and we'll go through each one of them and I would describe them and then sum up at the end. Okay, so I'm just going to switch here. It might be a little bit chaotic for a second. And we'll talk about number 1, which is the slipstream effect. Okay, so here we have an image of an aircraft, a Cessna 172. And I think, you know, in just looking at this video or at this photograph, you're going to quickly get the idea of what slipstream is. Now, slipstream is not a subtle form of adverse yaw. It's actually one of the more strong forces of adverse yaw that occurs in an airplane. Now, airplanes that are manufactured in North America and much of the Western world, but not all, the propeller spins from the pilot's point of view clockwise, okay, from the pilot's point of view. Okay, and from standing in front of the airplane, if you're looking at the propeller, it's spinning counterclockwise. All right, so you can see in the image here that the propeller is spinning in this direction, clockwise. Okay, so what happens is that the air that is pushed by the propeller is moved towards the left-hand side of the fuselage and spirals around the aircraft and eventually creates a force on the left-hand side of the vertical stabilizer, all right, which holds the rudder. And that causes the aircraft to yaw to the left along that vertical or normal axis. So as you increase power, you're increasing the slipstream, okay? And it winds around the fuselage of the of the aircraft. And the force becomes greater and greater against the vertical stabilizer, all right? So that is a very predominant force of adverse yaw that and many forms of adverse yaw are more noticeable at low airspeeds and high power settings. And this is a perfect example. So slipstream number one. The next one that I'm going to talk about, torque, is not so prevalent in light general aviation aircraft, probably more so in high performance, heavily loaded propeller airplanes, such as say a P-51, especially tail draggers, or a Spitfire or that type of aircraft. And that's torque. Okay, so torque is fairly simple to understand. Okay, so if you have the propeller turning in one direction, all right, the natural tendency for the airplane that's attached to the propeller is to rotate in the opposite direction because of Newton's law. I think it's the third law. Every action has an equal and opposite reaction. So as the propeller spins around, the body of the aircraft that's attached to the propeller wants to go in the opposite direction. Again, this will be more pronounced at high power settings and low air speeds, like say the takeoff phase. But really, this is limited to very high performance airplanes with high propeller loading, great big propellers, very powerful engines. And so you will now so if the propeller is turning clockwise from your point of view, then the airplane is going to bank in the opposite direction. And of course, it will pitch and it will bank and yaw to the left. So that's a form of adverse yaw. All right, that's the torque. Another form of adverse yaw is a little bit trickier to understand. It's called gyroscopic precession. Yeah, it's a little bit trickier, and it really applies mostly to tail draggers, but it does also apply to a certain extent to nose wheel aircraft. And this drawing here actually shows it quite well. Okay, so when force is applied to raise the tail of the aircraft, and of course that's done with the elevator, all right, what's going to happen is that the tail will pitch up and the nose will pitch down relative to that lateral axis I talked about along the wings, okay? So here's the thing about gyroscopes. They're very non-intuitive, all right? So probably many of you have played with gyroscopes when you're children or might have one on your desk or whatever, but anything that spins, all right, if you apply a force in one part, the result of that force will not show up until 90 degrees in the direction of the spin. In other words, if I apply force to the top of a spinning object, if I follow the direction of the spin 90 degrees, that's where the force will result. Okay, it's like it moves your force in the direction of the spinning object, the gyroscope. So if you think of a propeller, well, it has that precession. Okay, it has that precession. It resists the force where it's applied and applies that force 90 degrees from that point in the direction of the spin. All right, so here's your propeller. It's turning counterclockwise. All right, so if we apply an upward force, like say you want to raise the tail of a tail dragger before you take off, okay, which is standard, holding the stick to the neutral slightly forward position. As the aircraft gains speed, lift is produced, the tail comes up. Okay, what that does is it puts the force as if you were pushing at this part of the propeller. All right, tail comes up. It's like you're pushing, because this nose comes down along the lateral axis. It's like the force is being put there, and as the propeller spins 90 degrees, the resultant force happens in this 90 degrees from the top, which of course will yaw the nose and the gyroscope or propeller to the left. Conversely, if you lower the tail, then you're applying a force at the bottom, and that force will result 90 degrees in the direction of the turn, and the aircraft would yaw to the right. So yes, you can experience these forces in, like, say, a general aviation aircraft, nose wheel aircraft, like, say, a Cessna 172 or Piper or 152, whatever. These forces, although noticeable, are not huge. And again, it comes down to, the power of the engine. All right. So the more powerful the engine, the slower the airspeed, the more you're going to feel those forces. But just play with a gyroscope, you'll see what I mean. Play with a bicycle wheel that's spinning, and you'll see what I mean. So gyroscopic precession number 2. Oh, sorry, number 3. So now we're going to talk about probably the most common form of adverse yaw that you will experience flying your typical GA trainer, diamonds, nose wheel airplanes, diamonds, Cessnas, Pipers, and that's P factor. And this is one that does trip up a lot of people. All right, P factor. Okay, well, it all has to do with the angle of attack of the blade of the propeller. Okay, so as you know, a propeller has a bit of a pitch. Each blade has a pitch to it, and that's how it bites into the air and creates a backwards force, which then moves the airplane forward. Well, the way the propeller is designed and the direction of the spinning of the propeller is very interesting, because if you raise the nose, which you do during takeoff, you actually change the angle of attack of the downgoing propeller blade, which would be on the right-hand side of the aircraft. And as you increase the angle of attack of that side of that blade of the propeller, of course, what happens with increased angle of attack is increased lift. Well, a propeller is really just a wing that spins on the front of the airplane, pushes the airplane forward, or pulls the airplane forward. Okay, so as you raise the nose, you change the angle of attack of the propeller blade from a lesser degree to a greater degree, which means that that blade has more bite. Because it has more bite, it creates more thrust than the other side, okay, which is the upgoing blade, whose angle of attack, as you can see here, is reduced as you pitch the nose up. So you've got the left-hand blade reducing its angle of attack, giving less thrust, and the right-hand blade increasing its angle of attack, creating more thrust, okay? So when you pitch the nose up, the thrust is asymmetrical because the two blades have now changed their angles of attack. The left blade has a lesser angle of attack. The right blade has a greater angle of attack. And you can just take a little model airplane propeller and just tilt it up and down, and you can see the angle of attack change from the blades. So you create more thrust on one side than the other, the right side, in the case of raising the nose, which will swing the nose on the vertical axis to the left. It will yaw to the left. And of course, the opposite would happen if you put the nose down. Now, the left-hand blade of the propeller has a greater angle of attack than the right hand as you put the nose down, and you will have a yaw to the right, okay? So when people lift off, okay, and you raise that nose, you are giving the right-hand blade a greater angle of attack, which is going to want to yaw the aircraft to the left. And that's why you need to use right rudder to counteract that, to keep the airplane from yawing off to the left and eventually moving off to the left of the runway. So 1, 2, 3, 4. Okay, so let's go to number 5. Okay, number 5 is a very number 4 and number 5 P factor. Well, slipstream, P factor, and the next one are probably the most prevalent versions of adverse yaw that you're going to see in a general aviation aircraft, and you'll notice it right from your first flight. The other, torque and gyroscopic, with high performance airplanes, yes, but the general aviation trainers, not so noticeable. But this last one, I have 2 diagrams for this, are really crucial in terms of coordinated turns. Okay, so what do we mean by that? Okay, well, you've heard your instructor, if you've started flying, probably pound into your head the need for using rudder in the direction of the turn while your ailerons are being deflected. Okay, so it seems counterintuitive, but let me explain it to you. Okay, so if you take an aircraft and right now, if I'm flying straight and level, so here's the aircraft flying towards you, straight and level, okay, all of the lift from the wings is towards the earth, okay? So how do we turn an airplane? We don't kick it with rudder, because all we're doing is skewing the airplane in the air. There would be some bank, and that's because of aerodynamic factors and design factors. But for the most part, kicking the rudder is not really going to turn your aircraft efficiently. What we do is we increase the lift of one wing and decrease the lift of another wing, and the aircraft has now vectored that thrust horizontal. There's a horizontal component of thrust now, and the aircraft will fly in a circle in one direction or the other. Okay, that's how you turn an airplane. It doesn't turn like this. It banks and follows a circle. Okay, and that's because one wing is generating more lift than the other. Well, how do we do that? Well, we do that with ailerons. Okay, the aileron on each wing is in effect a control that it controls the shape of the wing, which controls the lift factor of the wing. So for example, if you're doing a right-hand turn, you can see that the left-hand aileron is deflected down. Why does that give the airplane more lift? Because it changes the shape of the wing and increases the angle of attack of the relative wind heading for the wing, okay, and creates more lift, which lifts that wing up. Now, conversely, this aileron has gone up. It's decreased the angle of attack, which means less lift on this wing, as I explained to you, and that wing goes down, and the aircraft will bank, in this case, to the right. But there's a phenomenon that occurs that is subtle enough, but can be demonstrated to mess up the coordination of a turn for an inexperienced pilot, or even some experienced pilots flying a new type of aircraft that they're not used to. And that is a form of adverse yaw, which we call aileron drag. Okay. Now, one would say, oh, I see where the drag is. You know, you're putting the left aileron down, it's hanging in the breeze, there's more drag. Well, to a certain extent, that's true, but that's not really where the drag comes. Okay. What's happening is the downgoing aileron here that increases the angle of attack of this wing, which lifts this wing, okay? And the upgoing aileron here, which decreases the angle of attack, which decreases the lift and drops the wing, create another effect, okay? And the other effect is called induced drag, all right? Induced drag is a function of lift and angle of attack. Okay, so you've all seen the videos of the big 747 or A380 landing on a misty day or taking off on a misty day, and you see these slips, these spiral wisps of moisture, looks like steam or smoke, coming off of the wingtip of each aircraft. Or when you see, say, a fighter jet pull into a hard climb or a turn, you will see these tendrils coming off behind the aircraft. Okay, those are actually an indication of they're actually an indication of induced drag. Induced drag is caused by increased angle of attack. As you increase the angle of attack of an aircraft, what happens is there's more pressure underneath the wing and less pressure on the top of that wing. Okay, and the air will flow from the high pressure up into the low pressure area in a spiral like a tornado, and it will, of course, build from behind the aircraft. Well, that's creating drag. It's it pulls on the back of the wing, okay? Because any disturbed airflow around any airfoil or aerodynamic design, okay, any disturbance is going to cause drag, right? It's like tugging on your shirt, okay? So if there is a vortex, all right, caused by induced drag on the left wingtip, it's actually going to apply a pulling force at the back of the tip of the wing. And what that does, of course, is make the airplane yaw in the direction of that pull. Okay, So when that aileron is deflected downward, it changes the camber of the wing, which allows it to create more lift, which increases the induced drag because there's greater pressure below and less pressure above the wing. Okay. And that creates the wingtip vortice, which then tugs and pulls on the rear of the wing, which then creates a yaw, which you can see from the nose of the airplane or out through the window to the left when you want to make a right-hand turn. Okay. So you're trying to turn right. You're doing everything properly. You're putting your control inputs with the aileron in. You're trying to turn right. And you'll notice this at high power settings and low speeds. Again, maybe a little bit of flap. Maybe your instructor can demonstrate this to you. If you don't combat the adverse yaw with rudder input while the aileron is deflected, you will notice that in the right-hand turn, the first thing that's going to happen is the airplane will yaw to the left a bit and then eventually come into the right-hand turn. It'll still be yawing a little bit to the left. In a sense, it'll be slipping. All right. And that's a function of induced drag. It's a function of increasing the power of the wing to lift, which creates more induced drag, okay, which then tugs at the back of the wing, which then creates a yaw. Okay, but here's the thing. It only happens when the aileron is deflected, which means, and as you know, you only deflect the ailerons to set your bank, okay? Once you've set your bank, you're putting the ailerons back neutral, more or less, and you're just following now with that horizontal component of lift, you're following around in a circle. So you're only using the ailerons to get into the bank and then neutralizing them. So that means that the adverse yaw for the wingtip vortices and the induced drag of the wing only occurs while the ailerons are deflected. Once you've neutralized the ailerons, that phenomena disappears. That's why when you're banking either left or right, you need to counteract adverse yaw with some rudder input, okay? So if you're trying to turn left, okay, and now your ailerons are deflected, of course, what's going to happen, so let's say right, just go with this, this image. When you're turning right, okay, you're increasing the left-hand wing angle of attack and lifting capability, and you have now induced drag and adverse yaw trying to pull it back. Well, that means that you need to also use right rudder to keep the aircraft in a coordinated turn while the ailerons are deflected. Once you've neutralized the ailerons, in other words, you set your bank, you don't need that rudder input anymore because there's no adverse yaw created by one wing lifting more than the other. And the same thing works for the left-hand turn, okay? So in the left-hand turn, the right-hand aileron is now deflected, okay? It's going to want to swing it's going to want to swing in the opposite direction, okay? In a left-hand turn, now your right-hand aileron is creating more lift, okay? Which is going to create more drag on that wing, which is going to want to yaw to the right, even though you're trying to turn left. So you need some left-hand rudder just while the ailerons are deflected, okay? So here's another image that you can see. So here we are, let's see, trying to turn left. Okay, so you can see that the left-hand aileron is down, the drag is increased, the lift is increased, all right? And so you want to turn left, but the adverse yaw, because this drag is pulling on the wing, yaws it to the right, okay? And conversely, you can see that you've reduced angle of attack, reduced drag, reduced lift on the left-hand wing. So in order to combat this adverse yaw, you need some left rudder, okay? So that's how that works. So there you go. You've got your 5 different types of adverse yaw. And like I said before, slipstream, you're going to notice quite a bit on takeoff, all right? Torque, not so much in general aviation airplanes. Gyroscopic precession, you will notice it on tail draggers, okay, especially very draggy airplanes with lots of power. But for the most part, on a GA airplane, it's going to be a nose wheel airplane. It's going to be fairly subtle. P factor, definitely, absolutely, no doubt about it. You can run off the runway if you don't counteract the left turning tendency of the airplane due to P factor. So that's very noticeable. And of course, with coordinated turns, adverse yaw caused by aileron drag is very prevalent, and you will notice it. It also reduces the performance of your aircraft. Okay. So anytime you're not coordinated, you're reducing performance of the aircraft because of different drags that get set up, form drag and parasitic drag and other types of drag. But induced drag is the one we're talking about here with adverse yaw from aileron deflection. So there you go. That's my little diatribe about adverse yaw with airplanes, and it's part of the art of flying is understanding these concepts and applying the corrective measures as you change the attitudes and movements of the airplane in order to be a really precise pilot. It's actually a lot of fun to understand this stuff and to get out there in the air and to see it in action and to use the corrective actions and see the results. It's really great. So yeah, so there you go. Adverse yaw. What we need in life is less head version, huh? Don't you think? All right, so that's the video for today, and I hope you have a great day. And I'll see you with the next thing I come up with, I concoct, and all the best, and tailwinds to you.